Hello, everybody. Welcome to our 10th Tech-Brunch already. Nice to have you here. I want to give you a short introduction what we are expecting today. So we are welcoming Michael Haller from the University of Applied Science in Hagenberg. Then we have Sarah, I hope I spell it right, Mlaka, yeah, right. And Roland Eigner, who are going to be here for us today. It would be great if you could join in at Slido with the hashtag Tech-Brunch. You can also join Slido in the browser. You don't need to install the app, but it's much more easier if you do it. And there you have the chance to put in your questions and also to vote up on questions that might be of interest for you also. Maybe you want to try it. We have a standard question already that you could answer to see if everybody's in. So the event code is hashtag Tech-Brunch, and our question for today for you is, do you work in the textiles industry? No. Yeah, and as you can see, there are two tabs. One is for the questions, and the other one is for this. So, okay, good. So today's topic is imperceptible textile interfaces, and I was happy to visit all of you in Hagenberg already, and it's really exciting. And if you have the chance, maybe you can sneak in there, I don't know. But it's really exciting to see what they're doing and what their research topics are. And yeah, I would say let's get started and have fun.
Yes, thank you for coming and thank you for the kind of invitation. Today we'd like to talk a little bit more about textile interfaces, and especially I would like to show you what we are doing in Hagenberg. Before we start, so we are working in the automotive industry as well. So this is a typical electric car, and one of the problems still is that the electric cars are still too heavy. Moreover, you might see a lot of elements there and a lot of buttons which are still made by plastic. And the idea is to reduce the weight on one side and to make it smarter. And ideally, you can integrate it directly, the sensor, into arbitrary material which is more touchable and which has a better feeling and a better sensation for human beings. And ideally, even your textile could be such an interface. So that's the vision which we have. And to do that, ideally, you come up with a sensor which can be easily and smoothly integrated in such materials. And this is what we are doing for a living. So we are developing right now a yarn-based sensor where the yarn itself becomes the sensor. And this was one of the early prototypes which we did. So you see a button, and it's a force-sensitive button here, which is just purely done with a yarn sensor. And this opens a lot of new applications which can be easily integrated in arbitrary objects. And you can see that there is no plastic at the bottom side. And this makes it really, really exciting. So this is what we do for a living. And today we'd like to give you a short introduction of what we have done over the past 3 years. Before doing that, I would like to share also what we are doing for a living in the Media and Action Lab, which is a research lab in Hagenberg. After my short presentation, we would like to give you also a little bit the possibility to show that you can implement your own sensor, which is not that complicated. And this is where Roland will give you a short introduction about a product-based sensor. And finally, we are working also on the development of new textile interface language. Because so far there are no design guidelines available, and we would like to show and to share what we have, what we found out there. As I said before, we are from Hagenberg. We are computer science building and department, as you might know. And we are coming from the Media and Action Lab, which is a research lab in the University of Applied Sciences. And we are heavily working on HCI interfaces. So human-computer interfaces, it's something what we are doing for a living. And I would like to start a little bit about the history, because it shows also the evolution of why we are doing what we are doing right now. And actually we started with something you might know nowadays, which was virtual reality and augmented reality. So we did that from 97 to 2003. So this was the area where nobody cared about VR and AR. And we were doing mostly applications for the OMV company, and especially for training and for education purposes. And then augmented reality became popular in 2000, and so we dived into that area as well by using tablet PCs. At that time, we didn't have the iPad yet, so it was really bulky, it was really heavy, and we had to mount our own camera at the backside. We were also thinking about mobile solutions, so this was the iPack. So how many of you still know the iPack? You're young. So the iPack was a smart device developed by Compaq several years before the iPhone came out. It was actually it was an iPhone without the phone capabilities. And what we did, we attached the camera at the backside, and then we did some augmented reality applications for IKEA furniture, for instance. This was the time where we had the Nokia phone, by the way, just to give you a short sense of how the phones looked in the past. So this was, by the way, the area where people asked us if this would even possible on a mobile phone, and with such a device, I said, no, not at all. It will never become real. So I'm wrong. So we also did work by using HMDs, and this brought me actually in a dilemma, because if you wear a head-mounted display for really a long time, you might find out that this is not a device you would like to wear for the entire day. And then I found a person which inspired me a lot. And I think we all need these kind of people. And his name is Junrei Kimoto. Junrei Kimoto is a person from Japan. He's from Tokyo University. And he was working for Sony CSL. And if you want to know a guru, so Tesla is one who invented the copy-paste. He passed away last week. And Junrei Kimoto is one of these people. And if you're working in smart interfaces, you must know him. And I would like to share a video with you, which was really inspiring for me, and it was a kind of door opener, also in a new domain. And what you see now is done in 1999. So it was really, really inspiring. So I would like to share this video with you. I think we also have audio, so I think it's okay.
By extending the concept of pick and drop, we have constructed a collaboration environment consisting of a digital table and a digital wall. In this environment, when participants bring their own notebook computers, a video camera mounted above the table recognizes them and their positions by reading attached visual markers. As a result of recognition, the table surface becomes an extended workplace for each notebook computer. For example, the technique called hyper-dragging allows a user to seamlessly drag an object across the boundaries of the computer displays. When the cursor jumps to the table surface, a line is projected to show a connection between the cursor and the notebook computer. The user can also move data from the tabletop to the wall screen. We can pick and drop by using a laser pointer. We call this pick and beam. Physical objects, such as notebooks or VCR tapes, can also be a part of this environment. The user can drag a digital picture to the physical booklet to make a binding between them. Then, the user can move digital data by moving physical objects. In this sample application, users are simulating the layout of furniture on the table. Participants can search for a furniture model name on their notebook computers, then drag it onto the table. They can also use a paper furniture catalog and directly drag a piece of furniture from the page. Finally, a mock-up camera is used to inspect the results of the layout. A VRML model is dynamically created and displayed on the wall display in accordance with the current position and orientation of the mock-up camera.
I found this really inspiring because you have to imagine this was done in 20 years ago. And if you would show such a thing nowadays, I think people are blown away still. And you have seen the bulky hardware they still had, but super inspiring. So the barcodes you have seen was an invention which was done exactly in this project. Also marker-based tracking. So this was invented by Junrei Kimoto. So everything which we know nowadays, which comes from Sony, was invented by Junrei Kimoto. So a really inspiring person. And actually, this motivated me also to go beyond head-mounted displays and to go towards smart environments. So we were using projectors and we were projecting content underneath and on walls and displays. And we were primarily interested in developing smart applications which should help you to sketch freely and to recognize objects, which can be then dragged and dropped quite easily. So this is what we did for a while, and we were always using these special pens, which were pens from Anodo. And then the iPhone came out, and everybody was requesting for a touch interface, and we just had to say, well, it's not possible yet for a large-scale display. And so this is why we were motivated to implement our own sensor, which should be easily integrated into wall displays. And so we started together with Ionim Research to develop a new sensor, which is based on a piezoelectric sensor. And this sensor is really reliable on the one side, and it's also able to track pressure, which was important for us. And then we found out that this sensor itself has also the capability to be used with bending gestures. So you could also bend the film. And this was even more better. So a flexible sensor was then the next big thing for us. And we started a project together with Microsoft Research where we developed a cover which can be used in combination with a tablet PC. In this case, it was a Surface from Microsoft. And with this overlay, we were able to do additional input based on bending gestures. And this project was then also used for bendable smartphones, which you can get nowadays on the market. Good. And this was actually the next big thing because we thought this bending was really neat and really nice. But there was still one problem. It was this missing of stretchability. And we found out that this can be solved by using textiles. And this is where we are right now. And the rest of the presentation is just about smart textile interfaces. We are not the only one in the world working on smart textiles, as you might know. So one of the most well-known projects in this area is the Google Jacquard from Ivan Popirev, who was, by the way, working for Junrei Kimoto. So all the people were always working together. And Ivan Popirev is also the person behind the Pixel phone, which you might know, which is on the market. And Google is still working on this product. So there is a small smart sensor which can be easily attached to your garment. And if you see this, and you see it also here in real. So I have 12 yarns which are woven into this textile. And what you can see here is that I have a touch interface, which is capacitive-based. So it's the same as what you have on your smartphone. And what you can do there is you can control your music player and you can define different shortcuts for triggering your iPhone app. There's nothing rocket science about the base of this Google Jacquard jacket. The only thing they have underneath is special yarn, which is a bundle of different copper threads, and they are just isolated with additional threads around it. And beyond that, the sensor itself is based on a capacitive-based tracking device, so it's not so complicated, and it's limited to 12 yarns. So you can just do a brush in or brush out. You can double tap it. So it's really limited. But there's an additional project done with Louis, with Saint Laurent, and actually next week they come up with a new product which will be done together with Adidas. We don't know yet what it is, but there will be something exciting because they do that also together with the FIFA Electronic Arts. Then there are other smaller companies like the Sensoria socks, which you can get on the market. It's a step sensor, so it's just counting the steps while you're running. And you again have a special device which you can click onto the socks. And underneath there are 3 pressure sensors which can be sewn on the socks. So what are we doing at Hagenberg in the field of smart textiles? Well, we started just to get a little bit more sense about what's going on with smart textiles. What can we do, seen from a computer science perspective? And so we went to different domains. We were working on steering wheels to have a pressure-sensitive steering wheel. We were going towards optimizing prosthetics. And finally, we were also interested in having garments which can be used as an input device, which is beyond the Google Jacquard approach. Basically, there are 3 ways of how you can sense the pressure. So either you do that optically, you do that capacitively, or you do that resistive-wise. And we primarily do it resistive-wise. We are working in 2 different domains. So one is on surface input, and I would like to show you one example, which we can also share, which is the removement or the replacement of controls, which you can see nowadays in your car. And we did that for a concept car for BMW, and this is what the result was at the end. It's also a combination of lighting, so even the lighting comes through a monofilament thread, so it's purely textile-based. And underneath there is a pressure sensor, which is again a yarn-based textile input. And what you can do here, you can just simply draw some gestures and they are recognized. And once this note symbol is recognized, the music player is starting and so on. And beyond that, we are working on beyond surface input, which means that even deformations can be tracked. We did that together with Google Research. So in this case, you can see that we have a special garment on our body, and then we can learn the different gestures. In this case, it's for instance a twist, and afterwards we can learn it, train it, and recognize it again. Now we would like to share a little bit more details about how we did the implementation, because there are several possibilities, and the first approach which we are sharing with you is quite simple, and you can replicate it quite easily. We would like to start with, because we have an entire pipeline, and we are, at the end of the day, we would like to share also some of the insights and also some of the hardware devices which we have. The principle which we have is a really old one. It's called the force-sensitive resistor approach, and ironically, it was invented in 1977. So, by the way, this is somehow frustrating for computer science, but everything has been already invented in computer science in the 60s or 70s. And we are finding it again, even it's the same case in our case, because all the textile input which we are finding right now is existing in a different form factor. And basically the principle is quite simple. So we have 2 electrodes on the top and underneath, and in between we have carbon-based conductive particles. And whenever there is a deformation of that material, of this carbon-based material, we can measure this by a smaller resistance. And I don't know how many of you are skilled with Arduino and computer science, but what we do at the end of the day is something really, really simple. We have a resistor, which is a reference resistor, and against that we are getting an input from the piezo resistive material, and based on that we can measure the difference, and we can actually say that this is this was more force or less force. And if you want to implement your own FSR sensor, the easiest way is to use a velostat, which is commercially available, and then you need an electrode, and you put this as a sandwich together, and then you have your own FSR-based sensor, which is a force sensor. So this is the very simple principle. So you just need 2 electrodes, and in between you need this special velostat material. So basically, and this is what you have seen also in the videos quite often, we have 3 layers, and 2 of those are of the same type. So basically, we have a conductive and non-conductive textile at the top and underneath, and in between we have this piezo-resistive material. And this is coated with carbon. And whenever there is a deformation, there's a deformation of this piezo-resistive material, and again, we can measure this by a difference of the resistor. So Roland will tell you a little bit more about the phenomena afterwards. The next thing you can do, you can embroider it on your own, and by using a special yarn which is conductive. So Roland will dive deeper into that area and will tell you how to do that. What you need is an embroidery machine. You need, again, this special piezo-resistive material as a textile, and on top and underneath you're using a yarn which is conductive. So Roland will tell you more about this later on. And finally, and this is our main dream, we have this implemented in a yarn. And this is what we did now. So we have a yarn which is coated with these carbon particles, and in the core is an electrode, so it's a copper. And once it's coated with this carbon, it has the same effects once you're applying two yarns which are crossing each other. So we have 2 yarns here, and they have an electrode in the middle, in the core, and then they are coupled with some copper, with some carbon. And if this is coated with carbon, it has exactly this FSR-based effect. The only thing you need is a cross point of these 2 yarns. And then you can sew it, and then you can actually implement a quite easy force-sensitive resistor with a yarn. We have it in different sizes. So the smallest which we have is 80 micrometers thick. And then we played with different thicknesses also because we wanted to weave it and knit it. So we sew it, we can knit it, and we can weave it. And this is super exciting because once you knit it, you have your own knitted piezo-resistive sensor, which is just textile-based. And then you can easily implement your own motion capturing garment if you want. Good. In addition to that, we are also focusing on hardware development and software sensing. So we implemented a prototyping board, which at this stage is still a prototyping board. This is why it's still thicker and bigger. It has the form factor of a credit card. And it can also be daisy chained, so you can actually trigger up to 64 by 64 threads or crossing points, which results in 4,000 sensor points, which is quite okay. And then you can daisy chain them together and scale it up. We have it in different form factors. So this is a different form factor because we are using this hardware also in combination with an embroidery machine. And the only thing is that you have to just place it on your embroidery machine, and then the machine does it automatically for you, and you don't have to do anything manually. This is then super exciting, but I think Roland will tell you more about this later on. And finally, we have also a signal processing pipeline done on Arduino, and then we have a C++ framework, which gives you also the possibility to hook into with OCR, and then you can actually, OSC, and then you can easily go to Unity and any arbitrary applications. So I would like to conclude this introduction presentation by showing you some live examples here. The only thing I need is a plug. It's now calibrating, and now this is a pressure sensor. In this case, it's different. So it's a super sensitive one. And in this case, we have a knitted solution from Coplater, which has 2 yarns, which are conductive. And in between, there's a velostat material. So this causes this piezo-resistive effect. This is the demo, which you can't see here quite well, but you see what's going on here. So this is a knitted solution by using our yarn. So this is the conductive yarn, which is coated with this piezo-resistive carbon. And whenever I apply a pressure here, you can see actually the peaks coming up here. So I would like to give them this to you. The only thing you have to be careful is that you just have the sensor either on this spot or on this spot. So if you press here, nothing is happening because we need a cross point. And finally, I would like to show you that our idea at the very end is to have a solution which can do both. So we would like to have a piezo-resistive sensor in combination with a capacitive-based tracker. And this is, for instance, a capacitive-based sensor which can be used also from the other side. It's a little bit hard, but you can see it now that it's getting green. And of course, I can also touch the backside of this material or have this hovering effect, which is something which we would like to have in the future. So ideally, we cannot just measure the forces, but we can also measure hovering and so on. And our hardware at the very end will support both. So right now we are working that. So that's it from my side. I think we are diving deeper now into the embroidery solution. And if there are any questions, I think we have 1 hour for that afterwards. Thank you.
Okay. Hello, everybody. My name is Roland Eigner, and I'm working as a researcher for the Media Interaction Lab in Heidelberg. And together with my colleagues Andreas Pointner and Thomas Breindl, I did a little research on embroidering resistive pressure sensors. And this work's going to appear at CHI 2020, and I'll give you a little preview about that today. So first of all, what are we trying to accomplish here? So we're trying to replicate force-sensitive resistors, or FSRs in short, on a textile basis. And force-sensitive resistors are actually electrical elements that change the resistance whenever external stress is applied, for example, when you press on them. So they consist of sandwiched foils, which with resistive polymer film, and interdigitated electrodes, which are pressed on top of that. They feature several advantages, which makes them quite useful for DIY projects. They are very low cost, they are easy to fabricate, they're very durable, and like I said, they're very easy to use. Even with simple driver electronics, you can use them as a simple voltage divider and hook them to your ADC on your Arduino, and you're basically good to go. So the basic principle of a common FSR is that you have two electrodes that are compressed onto a polymer sheet, which gives variable resistance depending on your pressure. You can see this on this illustration as RS1 and RS2 here, whereas the material resistance RV is more or less constant. And we replicate this by embroidering conductive thread on top of a carbon-based resistive sheet. So this sheet is, in our case, it's a weave that's based on fibers that are made of carbon-based material. These two electrodes are then connected to measurements electronics, which does then the actual readout and the processing of the data. Note that the electrodes do not necessarily have to be on top. Also, one or even both of them can be below this resistive sheet, which gives you more freedom in your design of your sensor layout then, and we will see this later. Here we see that there is, Michael already mentioned the principle with compressing the carbon particles, but there seems to be a bit of a disagreement about the way how FSRs work in detail. According to this paper by Weiss and Warren, it's what actually happens is that this polymer surface is kind of rough on a macroscopic level, and so they are in little contact with the electrodes. There is a little contact area, and whenever you compress those both areas together, and you increase the contact area, and this decreases the resistance, and that you can measure. And kind of turns out that this is also the way how our textile sensors work. So whenever you press with your finger on top of the yarn, you compress the yarn onto the material, and this gives you a significant drop on your resistance. Let's get a little bit into our motivation for this work. So we are coming from this angle of rather high density and high resolution sensor matrices that you get when you combine electrode grids like you see on the left. Already you saw this at Michael's slide already. And what you get is kind of a dense sensor grid and measurement grid. And it can do then things like posture tracking, like you see on the right here, works like that. But this is not always required. So suppose you have a grid like this with 3x3 fields, and you want to sense 3x3 fields. And you apply the traditional approach, and what you get is when you use these straight lines of electrodes vertically and horizontally, you get something like this. And when you imagine you have to set the scale of 10 by 10 centimeters, and you want to sense finger touch, then you get a lot of dead spots. So when you press in between, there are a few square centimeters where you cannot sense anything. And obviously what you can do is you can increase the number of electrodes you're using, but this also increases the complexity in electronics. It increases the amount of data you have to process. It decreases the sample rate. And maybe you're not even interested in this additional data, and you have to throw additional computational power on this to downsample. So this is a kind of a limitation, because also the size of the minimum actuator you want to track is dictating what number of electrodes you have to use. And what we're proposing is now to use space filling patterns. So you use the same number of electrodes, but you guide them over your area in a kind of winding manner. And so you fill the whole space and get a more or less uniformly responsive sensor across the whole area patch. And this brings us to embroidery. And why? Because embroidery is particularly useful for stitching arbitrary shapes and sizes. Also the workflow for designing those patterns, or maybe even auto-generating them and having them sent to the embroidery machine where it is then fabricated, is quite useful for rapid prototyping and for DIY. So here we see the machine we have in our lab, which can attach, in this case, this Hilbert pattern with up to 800 stitches per minute. So this is already quite fast. And here you see the resulting sensor patch, front side and back side. And note that on the right-hand side here, you see that the bobbin thread is only holding the electrode yarn loops in place. So this is what's happening here is that you only have actual conductive yarn on the top sides, and the back side thread is non-functional. So you have here a sensor, a single sensor with uniform responsiveness across the whole sensor area. You can fabricate this in many different sizes, and this you don't have to sacrifice any resolution or don't cause any dead spots. And what you can also do is you have huge freedom over controlling several design choices. You can link them, you can combine them at different scales. Here we see the meander pattern, which is inspired by Greek decorations. Note that for this pattern you have an intersection at the center, so the electrode traces intersect at the center. You don't see this on the lower image here very well because we had to use a different material here, which isn't transparent, but on the top one you can recognize it. This means you have to use alternating electrode layout. So one electrode has to go below the electrode, below the resistive sheet, and the other one has to go above. Well, so summarizing, we can tell that, coming back to our basic sensor design, we have a backing material, we have carbon-based resistive sheet, and we have conductive yarn, which is making up our electrodes. We saw that we have huge freedom in designing those patterns, and that we can also have different characteristics. We will see this later. But the question now is what value ranges will we get, and what are the correlations to actual physics, and do they even hold for this rather imprecise nature of textile manufacturing? Spoiler alert, yes, they do, but let's have first a look at at how an electrical resistor or conductor is really defined. So the resistance of a conducting object depends on the cross-section area A and its length, and also on a material depending constant rho. So this is quite intuitive. If you imagine a copper wire, the longer the wire is, the higher the resistance, which is why D is here at the denominator. And the thicker the wire is, the lower the resistance, hence A is at the denominator. And this fraction is then multiplied by the material's resistivity constant, which is rather high for an insulator like glass, obviously, and very low for a conductor like copper. Translating this to our textile sensor, we can see that the contact area is actually the trace of our electrode. And the cross-section area can then be approximated by the product of the length of our electrode times the thickness of our conductive material, which is here T. And here we see this mapped on a sensor patch. We can now go on and tell that material thickness is also constant, right? Because we use the same resistive material for all our sensor patches, because otherwise they wouldn't be comparable. So both rho and T are constant, and we can combine them to a single constant we call RS, and this is the sheet resistance. It's called what it's called in physics. So now we're interested in some actual measurements, and it turns out that yes, when we vary electrode distance D, then we get a directly proportional value in resistance. It's even strikingly linear, so this is even beyond what we expected. On the other hand, when we vary electrode length, then this is also in line with theory, we get an inversely proportional behavior. So just as the formula suggests. And this conformity is here, as you see, not as striking as with electrode distance, but it's close enough. And I think we can attribute this to textile manufacturing imperfections. It's just the way it is. You're never 100% precise. So in a nutshell, this means we can really calculate on this basis and estimate what the resistance will be of a sensor before we actually manufacture it, and we can even design our sensor with the capabilities of our hardware in mind. So furthermore, we identified several parameters that are also influencing the resistance of our sensors. First of all is stitch length, which is the distance between distinct stitches. And this is also quite intuitive when you recall the interface effect that I was talking about earlier. So when you use little stitch length, you stitch very densely, and the yarn is already in high contact with the material at rest. And when you press, you don't change much. On the other hand, when you use high stitch length, the yarn is quite loose, and when you press, you get a considerable response. So this is also something to be considered. And the next thing is what we call double stitches, which is when you stitch both ways. And for some pattern designs that we have, you have to use this. For example, on the lower left here, you see the IDE pattern. And there you have to go in and out all the time along the forks. You have to stitch both ways to get back out and go on to the next fork. Turns out that, this is also quite obvious that when you stitch more densely, you got more contact, you got lower resistivity. Also for electrode layering, same thing. Both electrodes are stitched on top. Then the contact is already quite high at rest. On the other hand, when you stitch both below the resistive sheet, the contact is much less. And also you can see on the error bar on the very right here that you get quite erratic results. In this case, when both are below, because the resistive sheet may even lift from the electrodes, and when the textile is slightly bent. So what we also investigated intersecting electrode traces, because they are inevitable for some of our designs, for example, for the meander pattern that we already saw earlier. And like expected, the patches with intersection show much lower resistivity because of this very close proximity at the intersection spot where only the resistive sheet is separating them. And however, the trend is, however, quite similar. So now let's go on and have a look at some actual space filling patterns that we implemented. So we chose them along several properties such as intersection count and ratio between single and double stitches. And obviously you can come up with many more of possible patterns, but we expect that this set has a good representative for every one of them. First of all would be the interdigitated electrodes trace pattern, or IDE for short, with many double stitches and no intersections. The second one is the bostrofidon, which is quite the opposite. So you have many intersections and no double stitches whatsoever. And you can already tell from the many intersections that you probably get a very low resistance here. The meander pattern, already mentioned as well, has a single intersection at the center, which is kind of suboptimal because it gives you non-uniform responsiveness over the area, so it's highly sensitive at the center compared to the other areas. The Fermat spiral avoids this by stopping at the very center before this intersection. However, this means when you want to link multiple of those, you have to stitch back out again, so you can connect to the next one. And this would end up with 100% of double stitches then, so this is also maybe unfortunate. Hilbert curve is a good compromise with no intersections and only double stitches on the lower electrode, this tree kind of structure here. In terms of scaling behavior, however, this is probably the worst because it always scales with a multiple of 2 due to this fractal property it has. It always keeps repeating itself. For the other ones, you can always add an additional loop and it gets slightly bigger, but this doesn't work for the Hilbert. In terms of characteristics, they all perform more or less the same. However, in vastly different ranges. So when I just to pick out the most outstanding one, which is the most to feed on, it's like expected. Got a very low resistance of 140 ohms, where it's starting at rest, compared to the Fermat, which with almost 10 times the resistance. And this may be something you may pay attention to when you depending on your electronics that you're using. So I would like to close with some lessons learned in terms of manufacturing, because this is also highly crucial. First of all, don't choose your stitch length too low, because not only would you cause small dynamic range, but also would you severely harm or even destroy your material. We see here a close-up of stitch length chosen of 1 millimeter on this Carbotex material, and it's even close to ripping. So this would render your sensor permanently defect. Second, consider also the back side of your patches. Keep in mind that the bobbin thread may pull the electrode loops out of place, and they may connect and cause shortcuts. So this is something to be aware of, and maybe even design your patterns with that in mind already, so you don't have your stitches too close to each other. Lastly, whenever the machine trims the conductive yarn, you unfortunately have to double check manually, and you have to post-process more or less with a scissor. There's always a lot of residue yarn, and there may even be tiny frails that cause shorts, even if you don't see them instantly with bare eye. So they are very hard to recognize sometimes. So this was it from my side. I hope you got also some interesting insights. And next will be Sarah with design aspects on textiles, interaction with textiles. Thank you.
Thank you. Okay, yes. So hi, I'm Sarah, also from the Media Interaction Lab. Roland went a bit more into the technical side of smart textiles, but of course, every time you need user input for anything, you also need to talk about interaction. So how do people know that this is even interactive? And of course, how do you interact with it? We kind of started with this more by the way than anything else, and we realized that there aren't really a lot of rules. Even basic design principles haven't really been tested or proved in textiles, so we kind of had to go very much into the beginning of this process to prove like the basics of what holds true in textiles, what can we sense only with our touch, what are some of the basics with which we can start to design textile interfaces. So we went very much into the beginning, and if you go very much into the beginning, you can't really keep specific use cases in mind just yet. So we focused on non-wearables because findings from that area could then be applied to more general stuff, including wearables, but also healthcare, entertainment, fitness, anything you can basically think of. We also had to be a bit careful that the interaction jump between what users are currently used to and what this new technology now offers, let's say, that this interaction jump is not too big. This is called the Maya approach, and it basically stands for most advanced yet acceptable type of designing stuff. And it goes into this so that, I guess we've all heard, this was too fast for its own time or something like this. It can be applied to whatever, but is applied to also design. So if you give people something that they're not used to, they will kind of reject it. You need to go into these baby steps, let's say. So we started looking by what are we currently surrounded with, and I guess you can imagine the most common interactive techniques today is sliding and pressing, and the correlating interactive elements, buttons and sliders, which is what we focused most on. Of course, there exists some textile interfaces already, some of them better, some of them not so good. But it seemed like they're all done kind of intuitively. There's not really a systematic investigation on what works and what doesn't, something that would give designers either a base point to evaluate something that already exists or a starting point for them to start developing their own textile interfaces. So we kind of wanted to set some basics on what will work and what will not that you can then take and do something else. So this project also correlated with a publication that will be presented at CHI. Also, Roland mentioned this. And we went with this project through kind of a filtering process that I'm kind of trying to visualize here. So we went through a lot of initial design assumptions on what would work on textile, what would not, what are some of the general design things that we would try out. I don't know, like does negative space work, or could it work? How would we do it? How could we apply hierarchy onto interfaces? What is more important? What is less important? There was a lot of these things, a lot of ideas. And then we sort of thought, okay, but there are people out there who do this every day and know more than we do, so let's just ask them. So we picked out 10 design assumptions that we thought were the most relevant, and we did expert interviews, with 6 or 7, with people from the academic side, but also from the industry side, and we basically asked them, what are you doing every single day? Do you think that this will work in textiles? Do you think that it will not? How can we translate this? And we got a lot of insights on what they think could work. Too much, actually. So we kind of picked out 5 statements that we thought were the most relevant and then tested them in a user study, out of which came the design recommendations. So I will present the design recommendations, and for you to be able to understand this, I will also have to explain the user study and the results that we got from there. And then if we want to go more into this, we can go into it later. Maybe a few words about the user study. So we did here in Linz, a few different public spaces. We had 30 participants, age varying from 17 to 65, very different professions, left-handed, right-handed. So while I will be talking about this, I'm going to be passing out the prototypes that we did, because everything is touching, and it makes sense for you to touch it. So this is the first experiment. Recognizing tactile contrast. It covers these 3 categories. So there was 12 samples altogether, 4 in each category, and it tested where is the limit between this contrast. So what do you recognize and what is too low for you to recognize? In terms of height, anything below 1.6 millimeter height difference was basically unrecognizable, or like maybe a few people recognized it, but 29 out of 30 altogether recognized the difference of 1.6 millimeters or higher. In terms of shape, it is angled between circle shapes. So a triangle between circle was very well recognized by 22 out of 30 people, while as we were kind of surprised that the texture was not so well recognized. I'm just going to go one step back here because this is relevant. So how we tested it was always one element was different in a set of 4, and 3 were the same. So I call this the default element. It had no added height. It was circular, and it had a texture that was kind of bland, like a polyester. You can feel it there. And we asked the participants which one is different, and they had to recognize this difference. And we were kind of surprised the texture was actually not very well recognized, but this is pretty good information, I guess. So leather was recognized the best, but only 13 people out of 30 recognized it. Everything else was even less. So the recommendation that comes from this is use explicit contrast to imply differentiation. By explicit, I just mean that you can use a height difference of 0.5 millimeter, but it might not be recognized by everybody or most people. But if you go for example, 1.6 or higher, then it will almost definitely be recognized. And the easiest is height, followed by shape, and then texture. The second experiment we did was smallest recognizable size. I have a few different ones, so I'm going to pass it on both sides. So we used the same 3 elements. It was a triangle, a square, and a circle in 4 different sizes, 4 millimeters, 6.5, 13, and 20. This kind of comes a little bit from Braille. So a Braille character is about the size of a fingertip, which is about 13 millimeters. So we kind of assumed that this would be the border between, oh yeah, here is something we can recognize, and here is something that we don't. So we asked the participants to not look at this, but only touch it and name the shapes that they felt. This basically proved that our assumption was correct. 6.5 was kind of still recognized, so by 50% of the participants, while as 13 or bigger by almost everybody, so 29 out of 30 people. So shapes should not be smaller than 6.5 millimeters, of course, if we want the user to recognize what it is. And the optimal shape size is 13 millimeters or bigger. The next one was convex versus concave shapes. And this was the only one that we put into a concrete example. So we asked people how they would interact if they would have to control a car window to go up or down, or sound volume to increase it or decrease it. We used 2 different use cases also because we were wondering if their answer would change based on context, which it did. It did just slightly, but it did. But the point of it was to prove, or to see if concave elements can also be perceived as interactive and how they go together. And it proved that they are interactive, could be interactive, and go very well as opposite commands. So concave surfaces are also perceived as interactive, and a combination of both can be used for opposite commands. We have to be, of course, careful of what is the use case of this. So this was also proven. It depends, right? Then the 4th one was influence of shape on interaction. This comes a bit from the theory of affordances. I don't know if you guys know Don Norman, cool guy. So he states that elements, or anything basically, should be designed in a way that only one way to interact with it is possible. So it's super clear. And we kind of wanted to test this. So if a circular shape, this was of course an assumption, does it make sense for the user automatically? Oh yeah, of course, I'm just gonna roll over it. It makes sense. And then if this is roughly the size of my fingertip, then I'm gonna press it, and I guess on a line, I'm gonna slide it, because those are the only possible ways. There were also some tricks here, because we wanted to see how right we are and how not right we are. So these 3 were proven to be very much buttons. Also, people just grouped them all together and answered for all of them. I would press all 3 of these. So this was 28 out of 30, which is a very high number. And then this one was intentionally designed kind of iffy. We were also not sure, but it was there to see exactly this. So people gave very different answers. 15 would slide, 8 would press. There was also options of, I would press here and press here to kind of go up and down, so kind of reinterpreting it as 2 buttons, and then maybe doing stuff like this, just very different things. So you can use the shape of an element to indicate required interaction, but you have to keep in mind what the user is used to. So what will be associated with, and how will we connect this element to the interaction technique? The last experiment was recognition of symbols. This comes from visual design, or graphic design. We weren't really sure if you would be able to recognize a shape purely by touching it and connect it with your visual memory and still know what you're touching. So if you're trying this without looking at it, and you can try to guess what it is, it's actually pretty hard. But we had this assumption of maybe it would work, so we still had to test it. And we used 4 icons that are kind of similar, not similar, like symmetric to one another and fairly simple and used very commonly in UI. So these are the star, the house, the phone, and the heart. Only half of the people, and this was still the highest number, recognize the star. And then everything from that on is basically, yeah, we proved that we cannot really recognize this purely by touching it. So design all shapes as simple as possible. This is something that has kind of stayed with me still after this whole project, and I think it might be one of the future possibilities of where this project could go on. So how could you then design icons? If they are obviously not visual, you would combine different tactile elements to it. So what would happen if you would add height and a texture difference and a shape difference and combine all these elements and start designing icons purely for you to touch? So this is something that's still an open question on how you could do it. So these were the 5 recommendations, and then we asked a few designers. We organized the workshop, and we asked them to basically try this out. Try it out in practice. Does it really work? Does it not? That was more of an R question. It was interesting to see they took it as a baseline and just immediately started with hands-on prototyping, either doing just individual elements or combining them into whole interfaces. Also combining these recommendations one to the other, adding stuff like if we would make it functional, then can this functionality also be a part of the design? Like how the element then connects to your hardware, can it be a part of it? They had 0 problems with what you see and what you touch. Yeah, just mix that together. Like it was really interesting to see also icons there, kind of. It was really interesting to see what they did, and it basically proved to us that what we wanted to achieve kind of works. So we've managed to give designers sort of a baseline, something that they can always rely on. Okay, this will probably work, this will not, something that you can step on and then build something else on, sort of to create other crazy things. Yeah, I guess that's it from my side. I guess this is still being passed around. Yeah, thank you.
Yeah, so thank you. I think this is really the first time we don't have any questions. So I guess basically most of your questions were already answered, or you got a good overview about their work. Is there anything you want to know that still up? No? Yeah.
I got a question. Especially the automotive examples, there's always the challenge of unique interfaces you can use by not looking at them. Because you should take care of the traffic as long as we still have to drive the cars. So there was a trend towards touch interfaces, and then there was a trend back to haptical feedback interfaces like knobs and stuff like this. So is this something that you've considered already in the textile interfaces, that there is some, I don't know, that you don't have to look at it to see if you really touched it, or you just tried to touch it?
It's a very good question. Actually, in the automotive, it's like this. So if you're driving a car for the very first time, you're watching to it. You're watching the symbol, and after the next drive, you should know it. And you're doing it blind, right? And this is the challenge, actually, because on the one side, you don't want to clutter it with too much information. And this is what we are looking toward in this project, for instance. One of the problems with the cars is that they are getting more and more features inside of the car, right? So it's like, this is why they came up with the touchscreen. And then they noticed that the touchscreen is not good because you have this jittering effect, right? And so you need haptic interfaces. Why we are doing it with textile and with other material is basically just to hide the information, because this is what the designers would like to have at the very end, so that it's super clean and clean up, so it shouldn't clutter you. On the other side, the challenge is really that there are more and more functions coming into the car, more features, and so you have to come up with some symbols. And so this brings me back to the question, it should be a ice-free interaction experience. But the next big challenge is also that maybe in the future the car is driving autonomously and you don't have to do anything with the car anymore, and you can do other stuff, right? And your surrounding can transform to a different input for something completely different, but not for driving. So these are the challenges which we have. And the point is, at the very end, we don't want to replace a button with a textile-based button. I think this would be absolutely wrong. Just replace a physical knob or slider with a textile-based one is not the way we would like to go. The other side is, okay, what's the next thing? Gestures, right? And I don't know how many of you are using the different gestures on the mobile phone. I still noticed just recently that the person found out, okay, the person has already the iPhone for more than 10 years and found out a new gesture, which is interesting, right? But this shows also that it's really, really complicated and really hard. So this is why we started this project, actually. This is why we started finding out a language, especially in our case, it's the domain of automotive. And we noticed that nobody so far cared about that, which surprised us, because we thought that there should be a kind of guideline book available in the literature, but it wasn't. Yeah. So, good point. We don't have a solution yet, but we would like to explore it. Also maybe with you. But very interesting point. And especially the car is so interesting because you have different people, right? The first experience with the car, and then you're on a daily life, you know how your car is working, and you would like to have an introduction from the dealer which is showing you in a 1-hour explanation how to deal with it.
Yeah, so of course, everything we do is textiles. So this was also tested on textiles. Of course, if you would use something really rough, maybe this would be the change. But also the question was, can you recognize what the specific shape is? So not only to say, okay, it's there, but also what exactly it is. Yes, it does depend on material. It depends also on what do you expect to find there, and also how high your tactile sensitivity is. So these are kind of, everything I said is kind of like a base rule, but you still have to keep in mind the specific use case on where you want to present it. So the material you would use probably would be some sort of a factor, but this was kind of the ground rule when you can start from, okay, on textiles, it's probably somewhere here. Specifically in the context of size, we can also say it probably will hold true in different materials as well, because in terms of the Braille alphabet, it was proven a very similar point. So we just kind of took that and translated it into textile, and it also holds true. But yes, things depend on context.
Good. Any more questions? No? Then I would like to switch to German. Unsere nächsten Tech-Brunches würde ich gerne noch ankündigen. Das wäre einmal Microtronics, Herausforderungen bei der IoT-Produktentwicklung. Das wird gehostet von Stefan Winkler, dann eben Marc Reis von Datron zum Thema Rapid Prototyping, von der Idee zum fertigen Werkstück. Datron natürlich, das wird sehr maschinenlastig, da wird es im Anschluss dann auch eine direkte Demonstration auf der CNC-Fräse geben, um das eben auch darzustellen. Ja, und dann die Anmeldungen wie üblich bitte an corporates@grandgarage.eu. Wir freuen uns über rege Teilnahme. Und dann möchte ich mich bedanken, auch vor allem großen Dank an euch, dass ihr euch die Zeit genommen habt, hergekommen seid. Und dann würde ich sagen, let's brunch.